Hi students, in this lecture we are going to start chapter 2, Power Series. Before we jump into the content, let me make sure that we are on the same page. So for chapter 2, we are going to focus only on Taylor polynomials. Taylor series, and some application. Well, by this I mean we are going to skip section 2.1, skip section 2.2, and skip section 2.5. Those sections were labeled in the course syllabus as self-study, so you can study it later if you want. But for the exam that is coming up this Friday, you are going to see only section 2.3 and section 2.4, which are Taylor polynomials, Taylor series, and some applications. Now let's look at section 2.3, approximating function with Taylor polynomials. So I will give you a motivation behind this topic. So first of all, let us consider the function that I have here, which is fx equal to the cube root of x to the fourth power minus 1. So in order to compute this function, it is not easy, right? Because you have to compute the cube root. So for example, if I say I want f of 2, it means I need the cube root of 16 minus 1, right? Which is the cube root of 15. So without a calculator, you cannot compute this thing by hand, right? It just seems impossible to compute this thing by hand. So the thing that we use to approximate the value of the function, this thing is called Taylor polynomials. So let's jump to the definition of Taylor polynomials. So Taylor polynomials. Let f be a function with the derivative of f up to order n defined at x equal to a. Then the n-order Taylor polynomial for f with its center at a, denoted by p subscript n of x, is defined by this formula. So this is the formula for Taylor polynomials. You can see that this is the Taylor polynomial of order n. Well, so we expand the polynomial up to the order n. That is the first thing you can observe here. Well, let's look at the examples so you have more idea about Taylor polynomials. So example 1. Well, we're gonna find the Taylor polynomial of order 0, order 1, order 2, and order 3 for fx equal to e to the x, center at 0. And then we're gonna observe the pattern. And the last question is that, can you give the Taylor polynomial of order n? Alright, so this is your first example, so I will go slow and hopefully you can follow me. Alright, we first have fx equal to e to the x. Well, in order to find the Taylor polynomial of order 0, 1, 2, and 3, what I'm gonna do is I have to differentiate function f up to order 3. Why is that? You will see it in few seconds. So first of all, I am going to differentiate this thing 3 times. So the first time I get e to the x, right? The second time I still get e to the x. And the third time I still get e to the x, because the derivative of e to the x, well, is always the same. All right, and then after that, well, I am going to compute f0, f prime 0, and then f double prime 0, and then f triple prime 0. This is just to, just get everything ready to plug into the formula. So this is going to be e to the 0, e to the 0, e to the 0, e to the 0, which is 1, 1, 1, and 1. All right, so when I have everything that is ready to use now, so well, let's go back to the definition of Taylor polynomial and see how to plug in. So the definition of Taylor polynomial is p subscript n of x. This is equal to f of a plus f prime a times x minus a plus f double prime a over 2 factorial times x minus a square, and then plus dot 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 plus the n order derivative of f at a over n factorial times x minus a to the n. Alright, we copy the formula here, and then now, well, the question asks you to find Taylor polynomial of order 0, order 1, order 2, and order 3. It means you need to find p0x, p1x, p2x, and p3x, right? So before we head to the part that we find the Taylor polynomial, so let's look at our center first. Every time when they ask you to find Taylor polynomials, so they're gonna give you a center. So this center is denoted by A. So your A in your formula is center. So here I'm gonna replace my center to be 0. So I'm gonna replace everything, well, in the formula by, well, replace A in the formula by 0. So this is 0, 0, 0, 0, 0, 0, and also this thing is equal to 0. Alright, this thing is Taylor polynomial, right? And then, well, let's look at P0 first. So P0, this is going to be the Taylor polynomial of order 0. It means you expand it until you get the 0 order, which means P0 is going to be just the first term. And then after that, if I want to do P1x, this is going to be the Taylor polynomial of order 1. So you have to expand until the term with degree 1. So that means you need the first two terms. Well, the Taylor polynomial of order 2, this is going to be including from the first term up to the third term, right? Because you need everything up to the term with second degree. And now, if you need P3x, you need to expand starting at the beginning up to the fourth term. Alright, so let's now look at the exact answer. So P0 is going to be just F0 here, which is 1. We already computed. So P1 is going to be F0 plus F prime 0 times x minus 0, which is 1 plus 1 times x, which is 1 plus x. And then P2 is going to be F0 plus f prime 0 times x minus 0, and then plus f double prime 0 over 2 factorial times x minus 0 square. So this is just 1 plus x square over 2. You can try simplify at home. And then after that you have f0 plus f prime 0 x minus 0 plus f double prime 0 over 2 factorial times x minus 0 square plus f triple prime 0 over 3 factorial times x minus 0 cube. So at the end you have 1 plus x squared over 2 plus x cubed over 6, right? That is how you compute the Taylor polynomial. And if you can guess what is your Taylor polynomial of order n, so I am going to give the answer here in the box. So the Taylor polynomial of order n, this is Pnx. It must be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right? And then plus dot 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 up to x to the n over n factorial. That is how to construct it, the Taylor polynomial of e to the x. Now let's look at example 2. Find the fifth order Taylor polynomial for fx equal to psi x centered at 0. Once you read the question, you can see that, well, we have a equal to 0. This thing is our center. And the fifth order Taylor polynomial means we need to take a derivative up to order 5, right? Because at the end, once you keep going with your differentiation, you need up to order 5 because you need fifth order Taylor polynomial. Alright, so what are we going to do is I'm going to start by fx equal to psi x, and then I'm going to differentiate 5 times. So f prime x dip psi, I get cosine, and then f double prime x, I get negative psi, right? And then after that, triple prime, so I differentiate negative psi, so I get negative cosine. And then after that, the fourth time I differentiate cosine, I get negative psi. And then with the negative psi in the front, so it's come back to psi x. And then the fifth derivative is going to be cosine x. Alright. Now I compute everything at the center first. So I have f0 equal to psi 0, which is 0. And then f prime 0, this is going to be cosine 0, which is 1. And then f double prime 0, which is negative psi 0, which is 0. And then f triple prime 0, this is negative cosine 0, which is negative 1. Now the fourth order derivative of f at 0, this is psi 0 equal to 0. And the last one we have cosine 0, which is 1. Alright, so now let's look at the Taylor polynomial of order 5. Well, this thing is going to be f at the center, which is 0, right? And then plus f prime 0 times x minus 0. And then plus f double prime at 0 times over 2 factorial times x minus 0 square, and so on up to the fifth order derivative of f at 0 over 5 factorial times x minus 0 to the fifth power. Alright, so I am going to replace the numbers we compute here. So the first term f0 equal to 0, right? And then the second term I have 1 times x minus 0. The third term I have 0, right? Because f double prime 0 is 0. The fourth term I will get negative 1 times negative 1 over 3 factorial times x minus 0 cubed. And then the fifth term I have 0, and the sixth term I have 1 over 5 factorial times x minus 0 to the fifth power. So after you simplify it, so you're gonna get x minus x cubed over 3 factorial plus x to the fifth power over 5 factorial. So this is called the Taylor polynomial of order 5 for fx equal to psi x center at 0. Once you know how to construct Taylor polynomial, you can use it to approximate your function. For example, well, let's look at this thing that I just have it on the notes. So let's say that we're gonna approximate the number e to the 0.1. So we can approximate by using the Taylor series of e to the x center at 0. And from example 1, we have that e to the x is equal to e to the x can be approximated by p subscript n of x, which is equal to 1 plus x squared over 2 factorial plus dot 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 up to x to the n over n factorial. So this is the Taylor polynomial of order n for e to the x. And then you can see that, well, if I compute the value of p sub n at 0.1, so I get the value in the table here. And then you can see that the value that we get is so close to the exact value e to the 0.1 with very small error. You can see that as n gets bigger, the absolute error decrease, and this is a good sign because, well, when you expand more terms in Taylor polynomial, it means you have better approximation. Alright, so now let's move to the next page. Now let's do more examples. Well, the examples 3 and 4, they are pretty similar to the exam you are going to see this Friday. Alright, so let's start by example 3. So find the quadratic approximation to the function fx equal to log x at x equal to 1 and use it to estimate logarithm of 0.98. So first of all, I am going to find the first and second derivative of fx, right? Because the question say I need quadratic approximation, so this means I need Taylor polynomial of degree 2. Polynomial degree 2, right? So that means I have fx equal to log x. I differentiate one time, so I have f prime x equal to 1 over x. I differentiate another time, so now I have negative 1 over x squared. Alright, next I have f1 equal to log 1, which is 0. So I need to replace 1 here because x equal to 1 here. This is our center, right? This is our center. So once you compute the derivative already, so you plug in as center because you are going to use it later. So this is going to be 1 over 1, which is 1. And then f double prime of 1, this is negative 1 over 1 square. This is negative 1. Alright, from here you can construct the Taylor polynomial of order 2 now. p2x, this is going to be f1 plus f prime 1 times x minus 1, and then plus f double prime 1 over 2 factorial times x minus 1 square. This is the Taylor polynomial of order 2. Taylor polynomial of order 2. Well, this will be used in quadratic approximation, and then after that we just plug in everything we have. So f1 is 0, and then f prime 1 is 1 times x minus 1, and then plus f double prime 1 is negative 1 over 2 factorial, which is 2, and then times x minus 1 square. So at the end you have x minus 1 plus, sorry, not plus, negative minus 1/2, right, times x minus 1 square. All right, this is your answer for the first part. So this is your formula that you use for the approximation. And now what you need is you need to estimate logarithm of 0.98. Here this is the Taylor polynomial of order 2 at 0.98, and that thing is 0.98 minus 1 minus 1/2 times 0.98 minus 1 square, right? You just plug in 0.98 into the x value here. All right, and then after that, if you compute everything, so you're gonna have 0.98 minus 1 minus 1/2 times negative 0.002 square, and at the end you're gonna get negative 0.0202. This is the quadratic approximation of log 0.98. Quadratic approximation. All right, that's all for example 3. All right, so similar thing with example 4. Let's use the second order Taylor polynomial to approximate square root 17. So they didn't give you a center, but we're gonna pick the center by ourselves. So we pick a equal to 16 as a center. So why do we pick 16? Because first of all, 16 is close to 17, and we can take square root of 16 and get a nice number, which is 4, right? That is how we pick 16 as a center. All right, so first I have fx equal to square root x. So because I have square root 17 here, so we decide to use fx equal to square root x because it is easy and easy to differentiate as well, and also, you know, the square root function is the one that we are looking for from the question. All right, so I have square root x, which is x equal to 1/2, and then if you differentiate this thing, so you're gonna have 1/2 times x to the negative 1/2, which is 1/2 times square root x, and then f double prime x, this is negative quarter times x to the negative 3/2. Well, this is negative 1/4 times square root of x cubed. All right, now we're gonna compute our function f, derivative of f and f double prime at 16. So I have f16 equal to square root 16, which is 4. You can see that this is a good thing that we pick a equal to 16 as a center, so we can compute square root easily. If you pick something like 15 or 18, it won't be easy like this. So after that, I compute f prime of 16, so I have 1/2 times square root 16, which is 1/8. And then f triple prime double prime 16, sorry, this is negative 1/4 times square root 16 cubed, which is negative 1/256. All right, well, we have everything on hand and ready to compute. So next step, I need the Taylor polynomial of degree 2, which is f16 plus f prime 16 times x minus 16 plus f double prime 16/2 factorial times x minus 16 square. And then once you plug in everything, you're gonna get 4 plus 1/8 times x minus 16 minus 1 over 512 times x minus 16 square. Alright, and then that means if you want to approximate square root 17, this thing is going to be the Taylor polynomial of order 2 at 17, which is going to be 4 plus 18 times 17 minus 16 minus 1 over 512 17 minus 16 square. Well, you have at the end 4 plus 18 times 1, which is 18, and then minus 1 over 512. Well, at the end, once you find everything, so you're gonna get this thing equal to 4.123. Alright, let's wrap up this video by looking at Taylor series. So Taylor series is nothing more than Taylor polynomial of order n. The different thing is that we just sum the terms infinitely many times. So which means for Taylor series, we're gonna add f prime a times x minus a, and so on infinite times. Just keep going. So you can see that we have no endpoint. So just f prime a times x minus a, and so on. And each term, the form is going to be the same as Taylor polynomial. Well, I have a remark here that a Taylor series centered at 0, this is called Maclaurin series. Sometimes if you see Maclaurin series, they are the same thing with Taylor series. Alright. Example 5. So let fx equal to cosine x. Find the Maclaurin series for f. So which means I have Taylor polynomial centered at 0, right? Write out at least non-zero 3 terms, and then write the series in the summation notation. Alright, let's do it. So because here we need at least non-zero 3 terms, so we're gonna differentiate over and over until we get non-zero 3 terms. So first of all, I have fx equal to cosine x, and then after that I am going to compute f0, which is cosine 0 equal to 1, right? And then after that I differentiate 1 time, so I get negative sine x, and this thing is f prime 0, so this is going to be negative sine 0 equal to 0. So it does mean that this term going to be 0, right? This term is 0. Well, once you expand the Taylor series, so the term that related to f prime, that term gonna be 0 because you have f prime 0 equal to 0. And then after that I differentiate 1 more time, so I get negative cosine x, and here I have f double prime 0, which is going to be negative cosine 0, which is negative 1. And then the triple prime here, so I'm gonna have sine x, right? And then that means the triple prime at 0, this is sine 0, which is equal to 0, right? And this term eventually gonna be 0, so we need one more at least. So the fourth order derivative of f, this is cosine x, and bam, this is good, because if you compute the derivative at 0, so you're gonna get cosine 0, which is 1. Alright, first we know that we have 3 terms now, non-zero 3 terms now, so we're ready to plug in into the formula and get the Taylor series centered at 0, or in other words Maclaurin series. Alright, so the Maclaurin series for f x equal to cosine x is it's going to be f0, right, plus f prime 0 times x minus 0, right, and then plus f double prime 0 over 2 factorial times x minus 0 square, and then plus f triple prime 0 over 3 factorial times x minus 0 cube, and then plus f to the fourth order derivative, and then add 0 over 4 factorial times x minus 0 to the fourth power, and then plus dot dot dot. You can see that as we compute before, so this term gonna go to 0 and this term gonna go to 0 because we have 0 here and 0 here. Alright, so if you plug in everything, so you're gonna get 1, right, from f0, and then minus, so f double prime 0 is negative 1, so you get negative 1 over 2 factorial times x squared, and then plus, well, the number 1 here that I circle gonna be this thing, right, and then you're gonna have 1 over 4 factorial times x to the fourth power. This is how we compute the Maclaurin series for fx equal to cosine x, and then you add infinitely times. Well, in order to write this thing in terms of the summation notation, you can observe the pattern. If you expand more, so you're going to see that this is 1 over 6 factorial times x to the 6th power, and then plus 1 over 8 factorial times x to the 8th power, and so on. So you can write in the summation notation by, this is summation of x to the 2n, right? N start from 0 to infinity, and then multiply this thing by negative 1 to the n, and then over 2 times n factorial. So you can see that here we have n start from 0, and the sign plus minus gonna be taken care from this term negative 1 to the n, and the term x squared, x to the fourth power, x to the sixth power, x to the eighth power, this thing gonna be taken care by x to the 2n. And then after that, you will see that the term 2 factorial, 4 factorial, 6 factorial, 8 factorial, this will be taken care by 2n factorial. So this is how we write the Taylor series in summation notation.